Okay, everyone, final video in the series, which is fast modular exponentiation, which is nothing but an application of converting decimals to binary, and some application of modular arithmetic too. Now, before I do this, I need to show you this very interesting phenomena, which is going to happen right now. So, if you do a successive squaring of a positive number a, did you know that it produced powers of 2? Well, it was a mystery to me as an undergrad too. Then I figured it out here. So if I have 3, okay, and I square it, I get 3 squared. I square it again. So I'm squaring the square, right? What is this? This is 3 to the power 4. How can I write it? This is 3 to the power 2, right? And pay attention to this, okay? Now, I'm gonna square it again. So 3 to the power 4 squared again. I get 3 to the power 8, which is nothing but 2 to the power cubed, right? And then I'm gonna square it again. So I get 3 to the power 8 squared, which is 3 to the power 16. Now I'm recording a video, so it's super clear because now you can just see it, right? Every time I square, I just need to add 1 to the power. Instead of multiplying it by 2, I just raise the power plus 1. So every time I square, if this is 2 to the power 0, it becomes 2 to the power 1, then it becomes 2 to the power 2, then it becomes 2 to the power 3, then it becomes 2 to the power 4, and keeps going. So look at this one. 3 to the power 1024 mod 7. What do you think? When will I end up with 1024? 1024 is 2 to the power 10, right? So I need to square this 10 times, and which is called fast modular exponentiation. I'm basically squaring the powers. If I were just to multiply 3 again and again, which would be slow modular exponentiation, to get to 1024, I would have to multiply 3 times 3 times 3 times 3 times 3 times 3 times 3 of 1024 or 2 3 times, right? Which is slow modular exponentiation. And we are not interested in anything slow. We want things fast. Fast modular exponentiation, you square the powers. So you're squaring at each time. So basically, 2, the power of 2, which is an exponent, is going to be increased by a plus 1 each time. Now, how does it make my life easy? Let's take a look. And it's going to be very, very similar. Similar type of question you can expect in exam. So I have 3 to the power 1024 mod 7. I need to calculate this. This looks scary. It's big. Even if you move the mod inside 3 mod 7, then do 1024 mod 7, it doesn't help you because 3 mod 7 is nothing but 3. Is the remainder of what's left when you divide by 7. Doesn't help me much, right? But let's see when I try to square it. Let's try to look for a pattern here. So 3 squared mod 7 is actually 9 mod 7, right? 9 is not that big, which is 2. When you divide 9 by 7, the mod function will return the remainder, which is 2. Okay, the next step is you square the thing. But 3 square is congruent to 2, right? So when I square 3 square mod 7, I can replace 3 square by 2, right? And you see how immediately it just became smaller, which is 4 mod 7. Now 4 mod 7 doesn't simplify, it's just congruent to 4. But I did something nice here. I did 3 2 to the power 2, right? Because 4 is what? 2 square. That, like I did here. If I square it again, look at the highlighted part. If I square 3 square, which is 3, 4, which is 3 to the power 2, right? And you'll see the pattern in a minute. Now, but I have to do it 10 times. But you'll see that each step, it's gonna get smaller. So next time, I'm gonna square the next entry, which is 4, right? So 3, 2 to the power cube mod 7 is nothing but 4 squared mod 7, which is 16 mod 7 is 2. I got 2 back. You see what is happening here? So now when I'm doing 3 to 2 to the power 4 mod 7, technically I'm just squaring the 2 again, the last entry, which goes here. Mod 7, which is 4. Make sense? Now I'm getting 4 back. So when I'm doing 3 2 to the power 5 mod 7 is basically squaring the 4 again, mod 7, which is 2. So when I'm squaring it again, which is 3 to the power 6, I can replace it by the 2 again, right? I'm basically replacing the last entry and I'm squaring it, which is 4 again. Do you see a pattern here? The 2, 4, 2, 4, 2, 4 keeps repeating. Now look at the powers of the power of 2 in the exponent. What pattern can you see? And that's the pattern which is important to you. So 3, 2 to the power n mod 7 gives me 3 values, right? It gives me 3. It gave me 3 the first time when the power was 0, right? 3 mod 7 is 3. So I have 3 options. It's 3 if n is 0. It's 2 if n is odd. And is 4 if n is even. So for 1024, I have figured out the pattern, and now I know that if I continue down this road, 3 2 to the power 10 must give me 4. And this is called fast modular exponentiation. You look at patterns and you figure out a repeating system like this. This will always be the case, and you go from there. Now we'll build on this because not always the powers will be nice, and 1024 was a nice number. 1024 was 2 to the power 10, right? Divide this by 2, what do you get? 5, 1, 2. So even if I gave you 3 to the power 512 mod 7 now, right? You would know that what is 3 to the power 512? This is 3 2 to the power 5, right? Mod 7. But now I know the pattern. So I know that if the power is odd, if n is odd, the answer is 2, right? So the answer is 2. So you have to do the work in the beginning, but then after that, everything becomes very straightforward. Now keep this pattern in mind, and let's solve this example. It's again 3 raised to some power, but the power cannot be expressed as some 2 to the power something, right? But what is a binary representation of 1135? You have to convert this 1135 into binary, okay? What Either do that, that's faster, or figure out powers of 2 that you can use. So I have the highest power I can use is 1024. Then if I add 64, then if I add 32, then if I add 8, if I add 4, if I add 2, if I add 1. This is 2 to the power 10 plus 2 to the power 6 plus 2 to the power 5 plus 2 to the power 3 plus 2 to the power. You see the pattern here? I'm trying to write this as a sum of exponent of powers of 2, and you'll see it in a minute. Why am I doing this? I'm doing it because I know the pattern, how the function behaves. If I write it like this is 2 to the power 10 plus 2 to the power 6 plus 2 to the power 5 plus 2 to the power 3 plus 2 to the power 2 plus 2 to the power, oops, it's 1, my bad, to the power 1 plus 2 to the power 0, right? And then I'm doing the whole thing mod 7. Now we have to be aware of some exponential laws here. If I have 3 to the power a plus b, this is nothing but 3a times 3b, right? And we know the fun property of modular function. This is, I can break it up. So this is 3 to the power 10 times 3 to the power 6 times 3 to the power 5 times 3 to the power 3 times 3 to the power 2, and continues until I'm done with all the. Now, this is a crazy example, but it's important so that you understand the material. Now, practice a few of these and match your answers with the answers given on the ASU website PDF. And make sure you get the right answer. Otherwise, you will never find a mistake before the exam. So, now I know how the modular function works, so I can bring this mod inside each of them. So this will be 3 2 to the power 10 mod 7, right? And this will be 3 2 to the power 6 mod 7. This will be 3 2 to the power 5 mod 7, right? And so on for all of them, 3 2 to the power 0 mod 7. And the final result will be again mod 7. So what is 3 2 to the power 10? We have to go back to the observation. If the power is even, I should get a 4. If the power is odd, I should get a 2. If the power is 0, I get 3 back. So power is even, so I should get a 4. Power is even again, I should get a 4. Power is odd, I should get a 2. Power is odd, well, I'm looking at this one. Power is odd, I should get a 2. Power is even, I should get a 4. Power is odd, I should get a 2. Power is 0, I should get a 3. Right? Multiply this. This is 4 squared. 4 squared gives me 2. This is 2 times 2 times 2 times 4 times 2 times 3, right? I'm just simplifying the chunks. This is 2 times 2 times 8. 4 square mod 7 is 16 mod 7, which gives me 2. 2 times 2 times 2 is 8 mod 7, which is 1, right? So I've got, again, I've got 8 mod 7, which is 1. So I've got the final answer 3 mod 7. And this is so much fun, right? You started with this crazy number and you ended up with just 3. Now I can make up an example for you guys and we can hope that that would work. So suppose I give you 5 to the power 1024 mod 11. Right? How the heck am I going to do this question? Think about it. Try the patterns, see what fits. Again, you need 5 to the power 2 to the power 10 to make 1024. So I started small, right? So I need to see the patterns. 5 mod 11, 5 mod 11 will just give me 5 back. What about 5 squared mod 11? Now, sometimes because I made this question right away, it might not make sense. And I'll just shut down the video if it doesn't make sense, which is 25 mod 11, which is 4. So that doesn't help me. So I'll do 5 squared, right? I'm squaring it again, mod 11. But what does that mean? I can move the 5 square with just 4, which will be 4 square mod 11, which is 16 mod 11, which is 5. Oh, this looks promising. Let's do a few more patterns so that we understand. Now again, I do 5. What is 5 square of squared? This is 5 2 to the power 2. If I do 5 2 to the power 3, that means I'm doing 5 4 squared, right? But basically what you'll do is you'll replace that with the 5. What is 5 square mod 11? It's again 4. So I can see a pattern. If the power is odd, I'm getting 4. If the power is even, I'm getting 5. I can stop it as soon as it starts repeating. And this is repeating right here. So I can see the pattern. If 5 to the power 2 to the power n has 3 values. Well, not really. If n is 0, or if n is even, then the answer is 5. If n is odd, then the answer is 4. So based on the pattern that we have seen, 5 2 to the power 10 mod 11, because n is even, should be 5. And this is how the fast modular exponentiation works. Now I'll give you a quiz on Tuesday. So you must watch this video. Okay, I'll post these videos on YouTube this weekend. Alrighty. Have a good weekend, everyone.